Waiting room. I think we can, yeah, let's wait 1 minute and then we let people in, I think. Actually, something needs to be said about the usefulness of Twitter, because I think this is, Kevin, this is probably the third or fourth paper that we have in VSET, because either I or somebody else sees people talking about the paper, and then, well, that sounds interesting. And, you know, we know you guys already, but, you know, it's useful.
Oh, interesting. Like, how did you hear about this on Twitter?
Either you posted something or one of your co-authors, or somebody.
I don't think it's me. I never made a Twitter account.
Somebody.
Then I guess
I'm very
that's
behind
Omer,
on
right?
social media. I the
I
only
think Omer
social
tweets
media.
a lot.
So somebody mentioned it. I remember that's where it comes from. Max, do you remember more precisely?
I don't remember on this occasion. I think because we invite, sometimes we invite just people and then they suggest titles, and this is how it happened with you. But sometimes we invite a particular.
No. The way it worked with Kevin. Kevin, I asked you for this particular.
I didn't know then.
Francesco, I think it's already time, no?
Okay, all right.
Probably,
sorry.
Yeah.
We'll figure this out later.
All right.
Okay, so are you admitting people?
Yes, I did.
Okay. Right, we're about to start. Just giving it a few seconds so that everybody's in. I think everybody's in. So welcome back to VSET. Today we have Kevin Hay, who's going to talk to us about private information. This is joint work with Fedor, Sandomirskiy, and Omer Tamuz, and we're very happy to have our panelists who are Doron, Ravid, and Weijie, Zhong. So just the usual rules, we're going to take 60 minutes plus approximately 15 for questions. There's also the virtual chair, as some of you already know. We're going to put the link again in the chat soon. We're definitely all going to move to, at least some of us are going to move to the virtual chair. Kevin is coming afterwards, so we can continue with discussion there afterwards. Finally, I just want to remind everybody that next week we have Francesco Squintani, who's from Warwick, who's going to talk about optimal overspecified contracts, and the guest panelists there are going to be Luca Anderlini and Alvaro Sandroni. Okay, Kevin, I think that's all, and the screen is yours.
All right. Thank you so much for having me at this seminar series, and thank you all for coming to this talk. I will be talking about private information. I'm joined with Fedor and Omer. So let me begin with a very familiar setup, right? Private information about a state of nature. Imagine there's a finite set of n agents, and imagine there's a binary state of nature omega, which is either low or high. And suppose that these people share a common prior probability p between 0 and 1 for the event of the state being high. Suppose agent I gets a signal Si about the state, which is usually called her private information. And we have a joint distribution P over the realization of the state and the realizations of the n signals, so the n agents, S1 through Sn, right? And this joint distribution defines the information structure. So far, I've said very little. This is like the basic setup of, incomplete information that we might find in an introductory course in game theory. Right? So what are some examples of such private information structures? We could have, for instance, public signals. Public signals are those signals where, each with probability 1, all of the agents have the same signal realization. We could also have, conditionally independent signals where, given the state of the world, the signals of the n agents are drawn independently across the agents. Now, let me ask the following question. Are the agents' information in these examples truly private? I mean, we call these things private signals, but are they truly private? Well, you might think that, well, of course, public signals are not at all private, right? After all, everyone knows the realization of the public signal. And so your signal realization is not private. Everybody else also knows that signal realization. There is also, though, a sense in which even conditionally independent signals are not very private, right? Suppose I have the two states being equally likely, and suppose I have binary signals which match the state with 3/4 probability. Before seeing my own signal realization S1, I, player 1, assign a 50-50 belief to the event that your signal is high. Right? But after I learn that my own signal is high, I now update my belief on this event. I now assign a higher belief, a 5/8 belief, to the event of your signal being high. So you see, I've learned something about your signal realization from my signal realization. Right? So in that sense, S1 actually contains information about S2. And so in this case, player 2's information is not fully private after all. I seem to have one question. Is this a question in the chat? Oh, no, it's not a question. Okay, thank you. Okay, so you might ask, what might it take for these private signals to be truly private? And I'm going to say a private information structure is one where the signals S1 through Sn are independent. Okay? Again, I do not mean conditionally independent. We already saw that conditional independence given a state does not actually give us this kind of privacy guarantee in the literal sense of the word privacy, but I really mean independent in the ex ante sense. So these private signals are things that contain information about the state, but not about each other. In other words, these are signals which do not update agents' higher order posterior beliefs. And agent I learns nothing about another agent J's belief from observing her own signal Si. Now, a first question you might ask is it possible for everyone to have informative private signals? At first glance, this might seem a bit paradoxical. I mean, how is it possible that the signal S1 is informative about the state omega? The state omega is correlated, with S2, and yet player 1 learns nothing about S2. But it turns out it is actually possible for everyone to have informative private signals. I'm going to give you many such examples. But there is something that's right about this question, right? There is indeed kind of a tension between, informativeness on one hand and privacy on the other hand. For instance, it really would be impossible for everyone to have, perfectly informative private signals, right? It would be impossible for everyone to have a fully revealing signal about the state, because then that signal, of course, won't be independent across agents. Indeed, this paper focuses on this tension between informativeness and privacy, and we ask, how informative can we make private signals? Now, why might you care about this question? Why might you care about how informative can I make private signals? Well, this is one application that we have in mind. This application relates to fairness, equity, and privacy in rating design. Right? So imagine the state of the world, low or high, refers to a borrower's creditworthiness. Okay, so this borrower will either return a loan or not return a loan. Imagine that in addition to this creditworthiness, the borrower also has another trait, S1, which is private or legally protected. This might be, for example, whether this person has a particular health condition. And this trait may be itself correlated with the person's creditworthiness. Now, there's a rating agency that knows both the person's creditworthiness as well as this sensitive trait, and there's a bank that knows neither. Now, the bank comes to the rating agency and says, tell me something about this borrower. And the rating agency wants to generate for the bank a signal S2 about the borrower. But the trouble is, there are some regulations or privacy laws which require whatever signal it is that the rating agency generates, that the signal must be independent of this protected trait S1. Why might there be such laws? Well, if you generate S2, which is independent of S1, this would guarantee that any downstream decision made by the bank on the basis of this signal S2 would be independent of the value of the protected trait, thus guaranteeing a fairness concept called demographic parity, that you will have the same distribution of decisions in different, for people with different values of this trait. Now, how does this relate to what I was telling you before? Well, if I think about the state, the creditworthiness, the person's health status, as well as this rating or the signal which is generated, for any rating which is legal, which does not violate privacy law, this object here is a private information structure, because I can view the person's health status and the rating generated as two independent signals about the person's creditworthiness, right? And here, this rating agency might be trying to generate a, signal which is as informative as possible about the person's creditworthiness without violating this privacy constraint. Okay? And so these results on how informative can private signals be give us a way to compute, what is the maximally informative such signal without that does not violate the privacy constraints. So here is the outline for today's talk. I will begin with a canonical representation of private information structures. I'll give you a way to think about all such information structures. And then we will turn to the question of informativeness. I'm going to ask how informative can I make these information structures? And I'll be defining maximal informativeness in the sense of Pareto optimality. That is, I'm going to be looking for those private information structures such that I can't give a Blackwell dominating amount of information to any agent without violating the privacy constraint. Okay. And finally, I'll sort of turn to this application I alluded to earlier about generating the most informative signal under the constraint of not revealing a protected trait. So let me immediately begin with an example of an informative private signal. Okay. So let us suppose that the state of the world, state of nature, omega, is high with 50% probability. This is how I'm going to generate signals of the two agents, 1 and 2. If the state is high, I'm going to choose a point uniformly at random from the blue set here. So by the way, if you can see this, I have the unit square over here, right? And I've sort of colored half of it blue. If the state is high, I'm going to choose a point uniformly at random from the blue set, and I'm going to give that point x and y coordinates as signals S1, S2 to the two agents. If the state is low, I will instead choose a point uniformly at random from the white set. And then I give its coordinates x and y as signals to the two agents. It turns out that this is equivalent to generating two independent random variables, both from the uniform distribution on 0, 1, and then using whether the pair S1, S2 falls into the blue set to determine whether the state is high or not. This is an equivalent description of the joint distribution between the state and the two signals S1, S2. And this equivalent description makes it clear to us that indeed S1 and S2 are actually ex ante independent. But also notice that both agents are getting a strictly informative signal in this example. Imagine you're player 1 and you have a signal that has the realization 0.9. Okay? What's your Bayesian posterior probability that the state is high? Well, you know your S1 is over here, yeah, at 0.9. And because S1 and S2 are independent, seeing that S1 equals to 0.9 gives you no information about S2. So from your perspective, S2 is still uniformly distributed on 0, 1. So you think that if S2 is any number that's 0.1 or higher, right, then the state is high. And so there's 90% probability the state is high after seeing a signal of 0.9. In fact, all of the signals here in this example have a literal interpretation, right? If you have a signal of recent realization of X, your Bayesian posterior probability about the state being high is equal to X. Okay. So this here is a first example of a private information structure, independent signals, ex ante independent signals for the two agents. You can't learn anything about the other guy's signal from seeing your own signal, and yet both signals are strictly informative about the state. Right. Here is another example. I've once again started with the unit square and I've colored half of it blue, but I've just done the coloring in a different way. Okay. And the idea is still the same, right? If the state is high, I'm going to draw a point uniformly at random from the blue set. If the state is low, I'll draw a point uniformly at random from the white set, and the X and Y coordinates are given as signals. Once again, this is going to be equivalent.
Sorry, is it possible to ask a question?
Oh, please.
Yeah, I don't, it's only a clarification question because I don't understand why you call it independent signals, because you draw the signals from a joint distribution. So given the value of one signal, you have the value of the other. It is because, it is a joint distribution. So they are somehow correlated or not?
It turns out that these two signals are independent of each other. That is, I can think about the conditional distribution of S2 given any value of S1. And that conditional distribution will be the same regardless of the value of the realized value of S1. It turns out that like when I say it in one way, when I say, okay, I draw it from the blue set, it might make it sound like they're correlated, but it turns out that they're actually independent. S1 and S2 are actually independent. You learn nothing about the other random variable from learning one random variable.
Okay, thank you.
They are, in fact, of course, correlated with the state. That's the thing. They're both correlated with the state. S1 and S2 are both correlated with the state, but they're independent of each other. Okay, so right, it turns out that this description is once again going to be equivalent to one where S1 and S2 are independent. Okay, IID generated from the uniform distribution on 0, 1. Okay, but it turns out, in this example, unlike the first example I showed you, right, signals no longer carry a literal interpretation. Right here, imagine I once again have the signal realization 0.9. What is my Bayesian posterior belief? Well, it's not 0.9 anymore, right? I sort of look at this vertical line that's above 0.9, and I realize that, well, the state is high if and only if S2 is at least 1/4. Therefore, if my sort of signal realization is 0.9, my Bayesian posterior belief is 3/4. If you look at this example, in fact, if you have any signal realization which is higher than 1/2, right, then you should have a Bayesian posterior belief of 3/4. If you have a signal realization that's below 1/2, you have a Bayesian posterior that's 1/4. Right. So what this picture is actually showing you is that this picture is actually showing you a binary signal structure, right, which induces a belief of either 1/4 or 3/4. One more example, but I guess you're sort of seeing the pattern here, right? Once again, I start with the unit square and I color half of it blue. I do the coloring in a different way. And it turns out, this example induces a belief of either 1/3 or 2/3, right? So if you have a signal realization that's above 1/2, if I look at how much of the vertical line above my signal is colored blue, that's 2/3. If I have a signal realization that's below a half, how much of it is color blue? Well, that's 1/3. Okay. And so the idea is really there is a general method, right, to construct these private information structures. The idea is, suppose the state is high with probability P and that there are n agents. What we do is we fix any subset of 0, 1 to the n with measure P. I'm going to call that subset A. If the state is high, I choose a point uniformly at random from A, and I give its n coordinates as signals to the n agents. If the state is low, I instead choose a point uniformly at random from the complement of A, and then I give its n coordinates as signals. This turns out to be equivalent to drawing, n IID random variables from the uniform 0-1 distribution, and then determining the state by whether the vector of such signals falls into the set. I think there's a question here, Arda.
Yeah, Kevin. So in all the examples that you gave, it is true that I observe my signal. I do not update my beliefs about your signal, but I update my beliefs about your beliefs about the state, right? So the second order beliefs move.
No, actually, you also do not update your belief about another person's belief, right? So if I look at this example, for instance, if I see my own signal S1 and I say it's 0.9, the issue is I do not know what your signal is, and your belief is your belief is entirely a function of your signal.
Yeah.
Does that make sense? The second player must see a signal, and that induces for them a belief, right? But yeah, I have no idea what your signal is because your signal is independent of my signal.
Yeah, I guess you're right. Okay, sorry.
Does that make sense?
Yeah. Thank you.
Yeah, so that's right. These signals, they do not tell you about other people's signal realization, and also not anything about other people's higher order beliefs. Good. So so I'm going to call this construction the canonical information structure associated with the set A. Right? I can consider doing this kind of construction for different A's. Right? I could vary the shape A, right? So in the unit square, I can consider this shape, or maybe this other shape, right? I can consider any arbitrary shape in the unit square. And as I consider different shapes, I'm tracing out different private information structures.
Kevin,
yeah, please.
So far there's nothing that prevents us putting more color on the square, right?
Absolutely, very good. There's nothing preventing us from putting more colors in the squares. Imagine we had 3 states and not 2. We should instead, if we have 3 states instead of 2, we could imagine coloring this, the unit square, some of it blue, some of it white, and some of it red. And then using whether the signal realizations falls into the white, blue, or red set to determine which of the 3 states is realized. And so that would be a way to generate private information structures when there's 3 states, and you can generalize this to any finite number of states. And this leads me to the next point, which is for now let's stick with the binary states case, but you might ask, is this just like a large family of examples as I consider different shapes, right? Or is this somehow everything? Is this all the private information structures that we can have? And that's the content of the next proposition. It tells you this is everything. What this result says is that for every private information structure, there exists an equivalent canonical information structure. That is, if you give me a private information structure about a binary state of nature, I can find for you a measurable subset A of 0-1 to the n, where if I do my construction from before, I would generate a private information structure where the belief distribution of each agent in the thing I generated matches the one that you gave me. Okay, so there's an equivalent one in the sense of each agent having the same, distribution of beliefs. And this result, by the way, also works if you have more than 2 states, in which case, you would instead of coloring the square with one color, you would color it with, m different colors if they're m different states.
Kevin, can I ask, is there an information structure that's private that you can describe relatively easily that's not canonical? So that, I actually have trouble figuring out what isn't something where you color everything in white and blue for two states.
You're saying what is not canonical?
Right. So we know that it's without loss of this result says without loss of generality, look at canonical information structures, because that's all we're good. Whatever you can do with anything, you can do with these. But I'm asking, it's like a revelation principle for.
I think I understand your question. So like, what's even?
The question is,
what's even ruled out, I guess, by canonical, right? So.
Yeah, exactly.
Let me tell you this. That's very good. So basically, the idea that we have uniformly distributed signals, that's not really a restriction. That's just sort of relabeling of signals. The key restriction is actually the following. Remember, I colored things. I didn't shade things. It's either 0 or 1. That's the key restriction. I colored things. So the state is fully determined by the signal realizations. Right? So I'm saying condition on the signals. Either the state is, if I tell you the two signals, either the state is either definitely low or it's definitely high. Well, in general, right, for general private information structure, the probability of the state being high given the signals, which I'll write as f of S1, S2, I mean, this could be some interior number, right? This could be like 60%. The state's high with 60% probability. Now what, right? Well, if you give me such a private information structure, what I can do is I can, come up with a new random variable. I'll call it S3, which is also uniformly distributed on 0, 1. What I'm doing with S3 is I'm using S3 to resolve the uncertainty about the state, which is left behind by the first two signals, S1, S2, so that the state is high if and only if the realization of this extra random variable falls below f of S1, S2. So remember, f of S1, S2 is the probability of the state being high given S1, S2. If this guy is like 60%, then I'm asking for this extra uniform random variable to be below 60%, and that's when the state is high. Okay, so now the state is fully determined by S1, S2, and S3. But wait a minute, I'm supposed to have a private information structure for 2 people, not 3. What do I do with this extra random variable S3? Well, what I do with this S3 is that I'm going to essentially split the realization of this extra guy, S3, among the first 2 players, player 1 and player 2, via a technique of secret sharing. I split this S3 into 2 shares of the secret, so that having one share of the secret tells you nothing about S3, but putting both shares of the secrets together, okay, can let you reconstruct S3. One way to do this is to let S3 be defined as the sum of 2 independent uniform random variables on 0, 1, mod 1. Imagine S3 is R1 plus R2 mod 1, where R1 and R2 are themselves uniform random on 0, 1. Then learning either R1 or R2 tells you nothing about S3, but having both of them together lets you fully reconstruct S3. So the point is, if I construct a new information structure where the first guy gets S1 R1, the second guy gets S2 R2, then I did not give extra information to any agent relative to what they had before in S1, S2. And yet now this bigger signal, this bigger profile of signals actually fully determines the state.
Kevin?
Yes.
So this construction, it looks very familiar. It's not exactly the same, right? Like to what we were used to, like the Borel isomorphism kind of stuff, where we can describe everything. And so I'm kind of wondering, have you thought about trying to describe non-private information structures in a similar way, by instead of having each of the SIs being uniformly independent, have just some distribution, let's say absolutely continuous respect to the big or something like that over the unit square.
Yeah, that's an interesting idea. Yeah, for the purposes of this paper, I guess for us this is like a preliminary result. We really want to get to the next part is perhaps the most interesting one. What we can say about these things. But yeah, you're right. Presumably a construction like this, some kind of graphical construction could be done for other information structures if we start with somehow correlated S1s and S2s, or in some sense. Yes, that's good. That's a great point. Yeah.
Kevin, I have another clarification question.
Please.
So after you've done this secret sharing, do you push everything back into two-dimensional space, or you allow this A to actually be in high dimensional?
In the end, you have to push it back, essentially, right?
Okay.
So in the end, I do want a which if there are two agents, then I'm asking for each person's signal to be a real number.
So you need to find a way then to reconstruct using S and R, right? Like combine
Right.
S and R into one dimension.
That's right. You're going to. That's very good. You're going to need some map from R2 to R1, basically. So you take the S1 R1, you push it back into a single dimension. Okay, so let's now move on to this next question about the second part of the talk, which is about how informative can I make these private information structures. So let me remind you of examples 2 and 3, right? In example 2, remember people were getting beliefs of either 1/4 or 3/4, and example 3, they're getting beliefs of either 1/3 or 2/3. And if you look at this for a second, you notice that wait a minute, each person's information in example 2 strictly Blackwell dominates her information in example 3, right? And so if you're in the business of trying to give out as much information as possible, we would never use example 3. Example 2 lets you give more information to each person without violating privacy, right? And so now we're led to this question of what are the most informative private information structures in this kind of Pareto optimality sense, right? So one thing you might ask is, okay, example 2 Pareto dominates example 3, but is example 2 itself Pareto optimal? Or maybe there's another way of giving information to these two agents such that each person gets a Blackwell dominating amount of information, right, without violating privacy. Okay. Great. And so I'm going to write down the following definition. So I'm going to say, for I and I prime, private information structures, I'm going to say I is sort of ranked above I prime if each agent's information about the state of nature in I, Blackwell dominates her information about the state in I prime. And I'm going to say a private information structure is Pareto optimal if it is maximal in that order. That's just another way of saying I can't give any agent more information in the Blackwell sense without violating privacy.
Kevin, there's a
Please.
couple of not really comments, but questions by comments in the chat. Jason says that these information structures are sort of like independent quantile space. And Elliot replied on Doron's question, and maybe related to Jason's, it would seem that you could represent any signal by pairing a copula with a state index partition of a unit cube. You want me to read those again?
I see. You can represent any signal by. Yeah, I'm reading them myself in the chat. Represent any signal by pairing a copula. Yeah, I think that's right. Yeah. I mean, yeah, you're right. I guess we're again, we haven't thought very hard about what this looks like for things that violate this independence constructor. But yes, we think this kind of graphical representation, something like copula should work even for correlated S1s and S2s for correlated signals. That's right. Thank you. Okay, so very good. Let me tell you about sort of how we figure out which of these information structures are Pareto optimal. And it turns out that the characterization of Pareto optimality lies or relies on results from a different field, and this other field is going to be tomography. So what is tomography? Well, tomography is an imaging technique that investigates the shape of an object by running X-rays through it. Right. So here's an example. Suppose I have like a potato in the middle. I'm trying to understand the shape of this potato. I have over here in yellow an X-ray emitter. what I do is I run X-ray through this potato, and in some parts of it, the X-ray will run through very little of the potato, so very little of it will be absorbed. But more towards the middle, for example, the X-ray will run through more of the potato, and more of it will be absorbed. And what we get by running X-ray is a lower dimensional projection, right, of the object that we're trying to study. And typically speaking, we have to run X-ray from many different angles to get a good understanding of the object's overall geometry. Here, we're trying to understand, for example, the circular object, and we're running X-ray from 3 different angles, producing 3 different lower dimensional projections. Now, there's this area of mathematical tomography that's concerned with the question of reconstructing the object from its lower dimensional projections. And within that area, there's this concept of being a set of uniqueness. A subset of 0, 1 to the n is called a set of uniqueness if its n projections onto the n coordinate axes suffice to reconstruct the object A. Okay? In other words, if I have some other set that matches the first set A in terms of all n coordinate axis projections, then that new set A prime A must be sort of the same up to a 0 Lebesgue measure. Okay, so some sets have this property, some do not, right? So if a set is uniquely pinned down by its n projections onto the n coordinate axis, it's called a set of uniqueness. Okay. How does this relate to what we were talking about before? Well, it turns out that this is precisely the characterization of what makes something Pareto optimal. Right? So the theorem is the private information structure associated with A is Pareto optimal if and only if the set A is a set of uniqueness. Okay. What this shows is, at least to us, an unexpected connection between 2 things that ex ante seem to have nothing to do with each other. Right? On one hand, we have an information thread concept, which is about the Pareto optimality of these private information structures, right? It's about there not being another way of delivering information in an independent fashion, which leads to black hole dominance in the amount of information. On one hand, this sort of information theory, and on the other hand, we have this sort of I guess geometric notion from mathematical tomography. And the result is claiming equivalence between these 2 notions. I'll discuss its proof later if there's time, but I think, as an application, let me just sort of tell you what we can do with this result, right? So as an application, right, recall that, we know that example 2 strictly Pareto dominates example 3, but, is example 2 itself Pareto optimal? Well, we can translate that question, right, into the language of this theorem. Because the question of whether example 2 is itself Pareto optimal becomes the question of, well, is this blue area from example 2 a set of uniqueness? Okay. Now, what does it mean to ask whether the blue area is a set of uniqueness? Well, this is like a problem you might find in a newspaper puzzle column, right? It is the question of, does there exist another coloring of the 4x4 grid which preserves all of the column-wise and row-wise counts of the color squares? You see, what I'm doing here is that I'm reproducing the figure from that example, right? And it's a 4x4 grid. And here I'm counting, right, how many cells out of 4 are colored blue, right, in each row and in each column. And the question really is, does there exist another way, right, of coloring this 4x4 grid as to match these marginal counts, right? As to have 3 color things in the first row, 3 color things in the second row, 1 here, 1 color thing here, 1 color thing here, 3 and 3. Like, is there a solution different than the first solution? After all, if there were another solution, then the set that we started with must not be a set of uniqueness, because then we would have discovered a different set with the same marginal projection. Okay. And if you think about this for a second, you realize the answer is yes, there are other solutions to this puzzle. Here is another one, right? I can sort of flip what's color in this corner, and I flip what's color in this corner. And I can continue to preserve. These row-wise and column-wise counts. Okay. But by our theorem, what this tells us from this, I guess, geometric observation is that what our theorem tells us is that the binary information structure, which induces a belief of either 1/4 or 3/4, is not itself Pareto optimal. Like we get this information theoretic conclusion that there must be another way of delivering information to two agents so that they both get independent signals and yet each person gets a black or dominating amount of information. Okay. Is there a question here? I'm trying to.
Yeah, there's a question in the chat by Jason
Okay.
again. Do you want to read it yourself?
Yeah, I'm reading it myself now. Okay, so is my intuition right? If it is a set of uniqueness, then there is no more information possible. So the interesting direction is the other direction. If it is a set of uniqueness, then there is no more information. So I mean that.
If you want to explain what you mean a bit, so that, I mean, unmute yourself and.
Yeah, sure. I mean, so you know, I guess the hidden information is the set A, right, in the tomography example.
Mm-hmm.
And if you know the set A, I mean, you know, if you run some lasers through it or whatever, then once you know A, there's nothing more to learn. There's no more information possible with running more lasers in some other ways or whatever. So you've learned everything possible about A. And so I guess the problem, and so, you know, you could have run some lasers and there's some ambiguity and you haven't determined A, and there are multiple A that you could get. But if once you have A, once you've determined it, there's no more information possible. So it seems like, and again, you can only have proof, right? And so I was wondering if one direction is like an obvious direction and the other direction is like where the work is. And so that was my intuition, but
so Jason, I think that direction, so it is true that if I know all of the marginals, all n marginals, then I know what. So there are two things. So first of all, the agents do know what A is. They do know the set A, which is used to generate the information structure. So that the set A, I guess, is common knowledge. There's no uncertainty as to what the set A is. Okay, so I guess there isn't a sense in which they're trying to learn what the big set A actually is, because they will be told the information structure that the information structure is generated from this particular shape A. So I guess I mean, and the other thing is, it's true that if I know all of the marginal projections, then I know A. But I guess these are also agents who are like seeing just their individual signals and not the n-1 other signals of the other agents. So I do agree with you that one direction of proof is not very hard, and I'll tell you how to do that direction. But I think it's not quite. I mean, maybe I don't understand the intuition you have.
Let's see the.
I will explain the easy direction towards the end. But yeah, I think it is indeed using very much the idea of set of uniqueness, but perhaps not in the same way you're thinking of. But yeah, but we'll get there.
So, Evan, can I ask?
Yeah, please.
Oh, sorry, Doron. You go.
I mean, I was going to kind of follow up on Weijie's additional colors kind of question. Yeah. So like a natural conjecture for a generalization of your theorem would have been that if I had more colors, I would need each set -1, because there's always one identified by the others that are all sets of uniqueness as being necessary and sufficient for.
Yes, that conjecture is correct. We actually showed this as an extension of the result in the paper. And so if you had like 3 states, for example, you have a partition of 0, 1 to the n into like 3 sets or something like that. You could imagine, projecting each of these 3 subsets of 0 to the n onto the coordinate axis. And there's a generalization which we call partitions of uniqueness. Like that partitioning of 0, 1 to the n into 3 sets, that partitioning is uniquely determined by the projections of the 3 partitioning sets onto the coordinate axes. That would be the that would be the generalized version, which we also show in the paper. Very good.
Thank you.
Kevin, could you just go back to the theorem?
Yeah. Here
Sorry.
it is. Sorry. Here we go.
Yeah. Yeah, okay. I was just wondering, so this characterization is in terms of the canonical representation of, or a canonical representation of a private information structure.
Right.
So I was just wondering whether, the answer is probably no, but I was wondering whether anything insightful can be said about what this requires of, a private information structure that isn't necessarily in canonical form.
That is a great question. Yeah, later on in a little bit, I will tell you about one way we can check whether, at least in the, there are things you can derive from this. But let's say you have, in the 2 agents binary states case, there is a way to tell whether something is or is not Pareto optimal, which is a corollary of the theorem, without first having to put into a canonical information structure. Basically, it's like I look at the CDF of the belief generated by one signal, and then I look at the CDF generated by the other signal, and they have to be related in a particular manner. But that result is going through in the middle, that I prove that result goes through this representation via certain sets. But I'll get to that in a second. But that's a great question.
Thanks.
Kevin, just another. I mean,
please.
If you feel you're out of time.
Should I stay on? No.
Yeah.
Should I stay on this slide, please?
That something kind of feels like it's connected, but I can't quite 100% see. Is going back to your like proof of the previous result. You had that step where you had to do secret sharing. And it seems like you could say, well, I'm Pareto optimal if and only if at that step there's nothing for me to do. Right? There's no, and that seems almost, it's not, I can't quite map it, but it almost seems like, that's the
excellent.
Is there
Excellent. So it is sort of related in the sense that if I had an information structure where given the signals, the state is not fully determined, like the state can be high with 60%, then I can tell you for sure that this thing definitely is not Pareto optimal.
Okay, good.
Because then the extra S3 signal, right? I can have some leftover uncertainty. I can give that to the first agent. Let's forget secret sharing. I just give everything to the first agent.
Right.
Then look, I gave the first guy more information.
Good. Okay.
But the issue is there might be some cases where there's nothing to do for secret sharing, and yet it is still not Pareto optimal, right? Like in example 3, for example, like there was nothing to do. There will be nothing to do for secret sharing, or even in this example down here, there's nothing to do for secret sharing.
That's right. Okay.
And yet it's still not like I can still somehow squeeze more information out of this, even though there's nothing left to do for secret sharing, right? And later on, we'll sort of at the end we'll see how to squeeze more information out of this. Okay.
Kevin, thanks.
Kevin, don't answer my question if I'm wasting your time too much.
Oh no.
I'm trying to get a geometric intuition for what these sets will look like. I'm sure you will tell us, but and sort of my first sort of guess was something like convexity and something like that. But it seems like it's a more general. It's a little bit weaker. Something like it doesn't fold on itself. There's no holes in the middle, kind of thing. Is that what it is?
Very good. I think all of these are going to be a part of the characterization I'll tell you about. I'll tell you about what these sets look like geometrically. You're very much right that this has to boil down to something about the geometry of these sets, right? And I'll quickly tell you what the geometry looks like. Okay, good. So now we know that we can sort of disprove the Pareto optimality of some information structure by just finding another set with the same marginal projections, right? That's what we did on the previous slide. How would we go the other way around? How would we prove that something is Pareto optimal, right? And the answer is, this is where it's helpful that we have built this connection, right? That we have built this connection to tomography, because it turns out that literature has established some results which characterize what these sets of uniqueness look like geometrically. Okay? I'm going to establish a few definitions to explain to you these results. So I'm going to say a set is upward closed if whenever a vector x is in the set, any other vector x prime which component-wise dominates x is also in the set. So for example, this one here, right? If I take any point in the blue set, any other point which is to the right of it and above it remains in the blue set. I'm going to say a set is additive if there are n of these bounded and non-decreasing functions hi, such that the set A is the set of those vectors where if I hit the ith component, okay, of the vector with hi and add everything up, I get a weakly positive number. And it turns out all of these additive sets are upward closed, and these are equivalent if n is equal to 2. Okay. So here's a characterization by Fishburne and co-authors. If n is equal to 2, every upward closed set is a set of uniqueness, and conversely, every set of uniqueness is upward closed up to a measure preserving transformation of the axes. So you're exactly right in thinking that it has something to do with something that feels like convexity or something else, right? Because these upward closed sets, if I look at these, they must be sort of right. They must be sort of convex. Okay. And okay, so basically, at least for n equals 2, like upward closed is an if and only if characterization of a set of uniqueness. Also, for larger n, at least we have sufficient conditions for sets of uniqueness. So every additive set is going to be a set of uniqueness. And this turns out to be almost sufficient in some precise sense. Okay, and so how does this theorem help us? Well, think back to example 1. The first example I showed you, that blue set is upward closed, right? If I take any point in the blue set, any other point that's to the right of it and above it remains in the blue set. So it's upward closed. By Fishburne and co-authors' results, this blue set must be a set of uniqueness. By our result, which says, this equivalence between set of uniqueness and Pareto optimality, this first information structure must be Pareto optimal. There's no way to give a black hole dominating amount of information to any agent without violating privacy. Okay. For any number of agents n, right, we can use additive subsets to generate, Pareto optimal private signals. And when there are two agents, like upward closed subsets give you all possible, belief distributions that you can have in these private information structures. Let me in fact come back to this question about, what are sort of corollaries or characterizations we can get without working geometrically, right? As a corollary, this is going to give us a simple test of Pareto optimality when n equals to 2. So let f be the CDF of a distribution on 0, 1 with a mean of p. Okay. And I'm going to define a new distribution, hat f, such that hat f evaluated at x is 1 minus the inverse of f evaluated at 1 minus x. Geometrically, this is saying that hat f is obtained by f by reflecting it around the anti-diagonal. Okay? And I will call such f and hat f, which are related by reflection around the anti-diagonal, conjugates. It turns out, here's the easy test. If you give me a private information structure, I can tell whether it's Pareto optimal by constructing the belief distribution given by the first signal f, the belief distribution given by the second signal hat f, and asking whether they're conjugates, whether I get one to the other by reflecting around the anti-diagonal. Why is this true? Remember, we know that if it's Pareto optimal, it must be given by this upward closed set A. But once you think about an upward closed set A, I guess something that looks like this, basically this boundary here is giving you what the CDF has to be. This boundary here is tracing out the CDF. In one direction, it's tracing out the CDF for the one guy. In the other direction, tracing out the CDF of the other guy. And so that's why the two belief CDFs must be conjugates to each other, like reflections in this sense, right? So that's relying in the background, the geometric characterization of upward closeness, but it's a result we can state here, right? This is a result we can state without referring to it's explicitly referring to canonical representations. Okay, so let me tell you about this application I alluded to earlier. Yeah, please go ahead.
So you gave kind of this, the previous slide is about like characterization of distributions of posterior beliefs, right?
That's right.
Now for a problem that's very related, information design kind of problems, very related to like distribution of posterior beliefs over binary states, is distributions of posterior means of a one-dimensional, variable or a state. And it seems this, it's almost screaming to ask. Suppose I have two CDFs of people's posterior means, and I want to force them to be kind of independent. Is this kind of condition enough for saying that there's no more information to provide a posterior means for these guys, or is there more conditions than that? Have you thought about that kind of problem at all? Or?
Yeah, that's a great question. We thought a bit about this problem. We don't have a clear answer. I mean, we have some examples of continuum states being given by but no, nothing very general yet. Okay. So let me just say, but that's a great question. That's a direction we should. Thank you. Good. And so let me tell you about this one application about generating the optimal signal given a protected trait, right? So, So again, to recall the setting, right? I've got this binary state of interest omega. I've got a sensitive or protected trait S1, and I'm going to fix the joint distribution between them. Okay. I'm trying to generate some signal S2, which is both like as informative as possible about this binary state, but at the same time independent of this sensitive or protected trait. Okay. It's equivalent to saying we're trying to find a Pareto optimal private information structure on the state and the two signals with a given marginal on omega and S1. Okay. And the proposition tells you that, first of all, this can always be done. There is, in fact, a Pareto optimal private information structure with any given marginal on omega and S1. And furthermore, it is unique up to equivalence. That is, there is a unique optimal, there's a unique signal S2, which Blackwell dominates any other signal about the state that's independent of S1. Furthermore, what are the belief distributions? Well, they are conjugates. Right? The best you can do is the conjugate distribution of the belief induced by S1. Let me give you an example, explicit example of how this works, right? So suppose I have a situation where we're trying to convey some information about the fit of a candidate for a job. It can be either low or high. And the trait that we're not allowed to reveal anything about is age. We have a binary measure of age. The person is either young or old. 50% of the applicants are good fit for the job. 50% of the candidates are old. And this is a job where like being old makes you a better candidate for the job. So conditional on being old, your probability of being a good fit for the job is half plus R. And that's the same as probability of conditional on being young or being a bad fit for the job. Okay. This R, some number between 0 and a half, is giving you in some sense a correlation between being old and being good at this job. I claim that this picture here shows you the optimal signal that preserves privacy. Why is that true? Well, first, I claim that it has the correct marginal distribution on fit and on age. Right? So let's just look at this. Why? I've colored half of the square blue, and these blue areas correspond to candidates who are a good fit for the job. Notice also that conditional on being old, okay, we have a half plus R chance of being a good fit. Conditional on being young, we have a half plus R chance of being a bad fit. I do have the correct marginal distribution. Also notice this blue set is upward closed, right? Take any point of blue set, take any other point that's to the right of it and above it, it's still in the blue set. And so that means by applying Fishburne et al.'s result and our result together, this tells you that this picture here must be associated with a Pareto optimal private information structure. I can't give more information without violating privacy. So what is this information structure saying? Well, can we just read out what it actually says? Well, what it says is that the most informative signal in this world, which does not reveal age, is trinary. The solution to this problem is trinary. right? The three possible signal realizations, we might label them as low, no information, and high. If you get no information, when you're in the middle here, you see you do not change your belief from the prior belief. You receive no information about this candidate's fit. But if you receive either the L signal or the H signal, that fully reveals the candidate's fit. You know for sure that either this is someone who is bad at the job or someone who is good at the job. Finally, notice that the probability of receiving this uninformative signal is 2 times R. Remember, R was this correlation between age and fit. And what this tells you is if this age is more correlated with fit, then less information can be sent about the person's fit for the job without violating privacy. So how much time do I have left? I'm trying to think whether I should talk about the proof or conclude.
Technically 1 minute, but
Okay.
you can take a few more minutes. Depends how long this proof is, but yeah.
Oh yeah, this proof is not very long. It's like two slides.
Okay, just do it.
Okay.
Do it. Go ahead.
Okay. So very good. Thank you. I will say a few words about how to prove one direction of this result. Right. So the key to proving this theorem here really is to show that if I indeed have 2 sets with the same marginals, such as the example we saw before, right? On the left-hand side, we have example 2. On the right-hand side, the evil twin of example 2, which has the same marginals and yet is a different set. Okay. Somehow, how do I use these 2 sets with the same marginals to build a new information structure, a new private information structure that delivers a black hole dominating amount of information? Well, as a first step, I'm going to take these 2 colorings of the square, and I will consider the convex combination coloring, which is a 50-50 mixture between these 2 colors. So what does that mean, right? So for squares which are colored in both of these initial pictures, it's clear that they should remain colored. The squares which are uncolored, it's clear that they should remain uncolored. But if a square is uncolored in one picture but color in the other one, then it becomes shaded. I'm going to view shading as half coloring. Okay, and now this is how I'm going to generate the state. Okay, I'm going to draw S1, S2, again, uniformly, independently on 0, 1. If S1, S2 lands in the color region, the state is definitely high. If they land in the uncolored region, the state is definitely low. But if it lands into the shaded region, what I'm going to do is I'm going to toss an independent coin. That's called the S3. And the coin toss determines the state. Right? So there's 50% chance of the state being high if S1, S2 should land in the shaded region. I'm going to claim that if I generate information in the state using this final convex combination picture, then I am generating the same amount of information for the 2 agents. So I'm ultimately trying to find something which Pareto dominates this example 2 that I started with. But I claim this thing here is at least equivalent. It generates the same amount of information for the agents as this first picture does. Why is that true? Well, if I think about getting the signal realization 0.9, with 50% chance I'm in here, in which case the state is definitely high, with 50% chance I'm here, in which case there's like 50% chance of the state being high. So in fact, I have a 3/4 posterior probability of the state being high. In fact, this is true for every signal realization, right? So this picture here generates the same distribution of beliefs as this picture over here. But wait a minute, remember, this final picture has this property that we talked about earlier, which is that now this picture has some extra information that can be squeezed out, right? This is a picture where the signals do not fully determine the state because there's this extra coin toss. What if I look at this coin toss, or what if I look at this picture, I toss the fair coin ahead of time and I tell player 2 how the coin lands. Okay, so I tell player 1 this first signal S1 as before. I tell player 2 the signal S2 as before, but I also tell player 2 how the fair coin lands. By giving player 2 the information about how the coin lands, I have given player 2 a strictly positive amount of information. And that's because with positive probability, it is a coin toss which determines whether the state is high or low. And yet, giving this extra coin information to second player did not generate correlation. I maintain independence. S1 and S2 are independent of each other, and this extra coin toss is independent of everything else. Okay? So in fact, by giving one of the players this coin toss information, I have generated an information structure which strictly dominates, right? Strictly Blackwell dominates the amount of information that they used to have before. And notice this construction very much uses the hypothesis that what I started with was not a set of uniqueness, right? Remember when I did this thing, when I did this convex combination coloring, the reason why that a positive share of the picture ended up being shaded, that's relying on the fact that this picture and this picture disagree on a positive Lebesgue measure. It is precisely when these two pictures disagree that this extra coin toss determines the state. So if you started with a set that is a set of uniqueness, this would not work. Okay, so let me, so Jason, I hope this clarifies how the set of uniqueness is being used to show that, if I start with something that's not a set of uniqueness, somehow I can construct something that generates more information for the agents without violating privacy. Okay, so let me quickly then summarize, right? So today I've told you about private information structures, which are those information structures where the signals of different agents, S1 through Sn, are unconditionally independent, ex ante independent, okay? And the first result was that, we can represent all such information structures as subsets of 0, 1 to n up to equivalence. Then I said, well, the Pareto optimal private information structures are associated with sets of uniqueness, those subsets which are determined by their projections onto the coordinate axis. So for example, these guys are not Pareto optimal because, right, they're not uniquely determined by their projections. There are other sets with the same projections, which are nevertheless different sets. We saw that for n equals to 2, a set A is associated with Pareto optimal private information structure if and only if it is upward closed. So things that look like this, right? And so if you have a pre-existing signal S1, we can show that the most informative S2, that is independent of S1, must induce its conjugate belief distribution. And we also know that for any n, additive sets are associated with Pareto optimal private structures. And that's all I have to say. Thank you very much.
Okay. Thank you very much, Kevin. That was really nice. Can I ask
Please go ahead.
Doron and Weijie if they have additional comments before we move to the virtual chair? I just shared the link, by the way, but Doron, Weijie, one of you?
So yes, I had one kind of thing, which is, everything you're kind of doing is leveraging your ability to kind of talk about this, or to construct basically a new underlying state space and work with that. Now, and this is very beautiful, by the way, and I'm very happy with this. The one thing though is that if I want to try to kind of implement, suppose I was that bank or whatever wants to reveal this extra, then I might not have the luxury of constructing the state space in this way. In the sense, I might be bound by what the real, like by let's say having to condition on S and omega, S1 and omega, or S2 and omega, which one is like the one that was private. And so let's say the best that I might be able to do is maybe add myself an independent kind of coin toss. Mm-hmm. And so the question is kind of like how easy it is to then implement your your optimal Pareto optimal implementation signal structures. When the only thing I'm allowed to do for deconstructing my S2 is to somehow condition it on like an additional.
Yeah, I think that will still be fine. I think basically, let's see now. What I am giving you is, this joint distribution, I guess, between omega S1 and S2, right? So somehow there would be a conditional distribution of S2 given omega and S1.
Good.
So if you're a bank that simply sees omega and S1 being realized,
I can then just toss my coin and kind of do.
Does that make sense?
I can just make sure that I toss my coin.
You toss the right coin in some sense. Does that make sense? Yeah.
I think so. I have to think about it, but that would be something like I think is worth kind of thinking about or pointing out maybe.
Yeah. That's right. Yeah. It does presume you can do the randomization, but.
Weijie, go ahead.
Oh, this might be a completely stupid question. If we require signal to be both conditionally independent and unconditionally independent, can we still do anything?
Excellent. Basically, no. I think the only thing that's conditionally independent and unconditionally independent, I think that's like you have to reveal all the information to one person and nothing to everything else, to every other person. Yeah. So I think you can have two people like having informative things if you require both.
Okay, I'm just gonna signal to Kevin that Jason has just posted a link to, well, not a link, but posted the title of a paper that he thinks either or should know about.
Oh, okay. Let's see. I'm trying to read it. This comment, it's very long. How the privacy results application of discrimination on protected relates to this. That takes the perspective online app platform that wants a signal advertisable each requires non-discrimination.
I can probably say it out loud.
Okay,
that's
please.
better. Yeah. So I guess in 2012, Dwork et al. Had this paper called Fairness Through Awareness. And the main application they had in mind was these ad platforms online. And they collect all this user behavior. So they know a lot of details about users. But and they want to give some of this information to advertisers so they can advertise to the right users, but they don't want to allow some kind of like redlining or other stuff like that.
Right.
So it seems like it has to be that they were after something like what you're calling private information.
That's right.
And so but the paper was like so many years ago that I only remember it very vaguely, and so I wonder if you know it, you can comment. But if you don't know it, then maybe I'll get a comment from you later.
Precisely, I do know that before this kind of this stuff. I mean, there was this idea of like, oh, maybe we can just, if we're trying to protect a particular attribute, let me just not include that attribute in the stuff I give you. But that's not quite right, because if you end up including perhaps correlates of that attribute, then that attribute can be somehow inferred, right? So somehow, if you want the stuff that you give to be actually independent of the attribute, that you can infer nothing about the attribute, and that's not just by erasing the attribute itself, but also erasing the correlates of it, so that you can't make any inferences about it. So in the end, the stuff that if you're doing this perfectly, then the stuff you're actually giving, it must be independent, right, of the realization of the attribute.
Yeah, that comment is basically what was I guess one of the contributions of this paper, which is the awareness part. The awareness part is like, you can't just
right, you can't simply say, I'm going to delete this column I don't want people to learn about, because if that column can be very nicely predicted by other columns, then it's not really deleting information contained in that
fact,
column,
if you don't use that column in doing your signaling, you're going to mess up.
That's precisely right. So if you look at, in fact, if you look at the kinds of things where the structure of the optimal S2s, it's using both omega and S1, right? It's using both the true state and the realization of this protected trait, right, to generate the S2s. And so you very much need to like the optimal information structure does have that property. So I'll definitely take a look at this paper and figure out thank you.
Okay. I have a question myself. which is not really, I mean, okay. So before, I guess there's two questions. So as you say, this needs to, for n equal to, this needs to be upward closed up to relabeling. So obviously you could you could change the colors, you can switch the colors, right? That's what you mean by that, right? You could.
That is what I mean by, yeah. Right. So well, by that's right. So for example, switching the colors, you know, for example, I could take, look at this set. This is upward closed, right? But of course, the white set is also the white set is also.
I was going to say, it seems to be that there's a property called downward closed.
Exactly. That's where the up to relabeling is coming from. So by relabeling, I mean relabeled 0 as 1 and 1 as 0, just flipping the axes. Basically.
Indeed, obviously, but for any n, is there, so upward closed becomes additivity implies upward closeness. So is there something such as anti-additivity? I don't know what it is that, or does additivity implies downward closeness as well? So I'm just wondering whether this relabeling thing is indeed true beyond the n equal to 2. I see. You're looking for the additivity. So let's go back to additivity. Well, I mean, so for 2, it's obviously. I understand your point. Yeah. So maybe there's a more. Oh, I see. Fun. Yes, I think that's true. Yeah, I think that's true. So basically, if you let me think. Maybe you just want it to be, certainly if you flip the sign to be less than equal to, I think, right? You're fine, that will probably give you that's right. That's right. So this is a sufficient condition for upward close, and you can repermute upward close guys in some way and still be okay. And so presumably you can repermute the functions in some way and still be fine. Okay. I'm probably gonna ask you another question in the virtual chair because Alexandros wants to ask a question. I'm gonna let him do that. Okay, great. So thanks a lot. And by the way, after sorry, you're muted. Sorry, if it's very quick because we have to move away from this. Alex, how long?
Yeah, it's very quick. So
I will stop recording.
Okay. So about the relabeling, that what Francesco just raised, but could you not, as in the example where you had 3 signals for S2, 3 states, could you not flip one of them, right? Flip the first one with the second one.
You're looking for this
exactly
this
here. Yeah, age for the empty set, for example, right? You could flip that, and then you would still have everything would be maintained.
I could flip that. So I see. You want me to color instead like flip the 2 colors basically.
Right, but then it wouldn't be upwards, whatever.
That's right. It would not be upward close, but it would still be okay because I mean,
and would be Pareto,
in that case. Yeah, that would still be okay. That would still be optimal. But in that case, it's just like whenever you get the L signal, you know the person's definitely good. Whenever you get H signal, you know the person's definitely bad. Right? Because if the stuff I'm coloring refers to the good people, then I
was just thinking of, instead of it being in the middle, right? The empty set being in the middle, it being up, right? The exact section. You move it up. Right?
That's right. That's right. So if this is empty and this is all color and half of this is color.
Right.
Exactly. I know what you're saying. So I mean, you know, these letters don't have meaning, right? Except in equilibrium. But you know, the meaning of H would just be, you know, you have your bad fit. The meaning of L in this case would just be your good fit.
Okay, I think it's time for all of us to say thanks to Kevin, and again, we really enjoyed it. We'll see you next week, and some of us are moving to the virtual chair. Kevin will be there.
Yep.
And thank you, Weijie. Thank you, Doron.
Thank you so much for coming to this talk, and thank you for the great comments.
But we'll see you again next